Limit Laws, Part 2. Sometimes for particularly tricky limits, we like to apply something called Squeeze Theorem. So Squeeze Theorem is if f of x is less than or equal to g of x, which is less than or equal to h of x, where the f, g, and h are just arbitrary letters for the functions that we're using. So we could have used a, b, c in this theorem if we wanted to. When x is near a, except possibly at a, and the limit of f of x is equal to the limit of h of x, so that means that the limits of these outside functions are equal to each other, and they're equal to L, then the limit as x approaches a of g of x is also equal to L. And that's actually a different blue, so let me redo that line. So that means that if g of x, or some function, is squeezed in between two other functions who have the same limit as x approaches a, then that function that's being squeezed, the one in the middle, also has that limit. So this is a theorem that we apply mostly algebraically, but it might be useful to look at what this might look like. So let's say that we have this coordinate grid, and we have some sort of f of x. So this is some sort of function. And then we have some sort of other function, h of x, which is larger than f of x, but the limit as x approaches a is the same. So my function h of x is larger, but has the same limit, and I can actually make that touch a little better, has the same limit as x approaches a. And then I have some other function that is squeezed in between these two functions. So it's greater than f of x, but it's less than h of x. So it can be doing any crazy thing between these two functions, but as it approaches a, it gets squeezed in between these two functions. So if we can evaluate the limits for f of x and h of x, and we know that g of x is between them, we can also find the limit for g of x because it's being squeezed. So there are those two main criteria that are necessary in order to use Squeeze Theorem. You have to have a function that is squeezed between two other functions, and those outer functions have to have the same limit. So here's a few non-examples, just looking at the picture, where it might pretend that you can use Squeeze Theorem, but it fails one of these two criteria. So, for example, you might have an f of x and an h of x, so these two outer functions. And it might be that the limit as x approaches a is equivalent for both of these. So we have those equal limits. However, g of x might not actually be between these two functions. And if it's not between these two functions, then it's not actually squeezed. So even though they have equal limits, that doesn't mean that this other function has the same limit. So we couldn't apply Squeeze Theorem there. Another example is it's possible to have some sort of f of x and some sort of h of x with a g of x squeezed in between them, But if we look at a, the limit as x approaches a is not the same for those outer two functions. So you might have a function that's squeezed between two functions, but might not have equal limits. So it's not squeezed quite enough. It's between them, but we couldn't use squeeze theorem. Now let's take a look at an example. So we have if 3x minus 3 is less than or equal to f of x is less than or equal to x squared minus 3x plus 6, for x is greater than or equal to 0, find the limit as x approaches 3 of f of x. Now, we're trying to do this, so that means we need to make sure that this scenario fulfills the different conditions to apply squeeze theorem. So first we have to show that f of x is less than or equal to g of x is less than or equal to h of x. But that just means we need to show that the function that we need to evaluate the limit for is in between the other functions. And of course, that has to be near a. The other thing we need to show is that the limits of the outside functions are equivalent. So let's do that for this problem. Okay, now this one's a little bit tricky in some ways, because in the definition we go f of x, g of x, h of x for our three functions, but this one has f of x in the middle. So I'm going to color code this to help us keep track of our outer and inner functions. So our lower function is this 3x minus 3, which is less than or equal to this middle function, an unknown f of x, which is less than or equal to this upper function, the x squared minus 3x plus 6. And this relationship is true for x is greater than or equal to 0. And since a, this number that x is approaching, is greater than or equal to 0, that means that we have f of x is less than or equal to g of x is less than or equal to h of x, that first part of the definition that we need for squeeze theorem. So the next thing that we need to do is show that the limit as x approaches 3 of 3x minus 3 is equal to the limit as x approaches 3 of x squared minus 3x plus 6. So we need to show that the limit of our lower function is equivalent to the limit of our upper function. And we'll do this by evaluating each of these limits. So let's start with the limit as x approaches 3 of 3x minus 3. Since 3 is in the domain of 3x minus 3, which is a polynomial, we can apply direct substitution. So we'll substitute that 3 in for x. So this limit is equal to 3 times 3 minus 3. 3 times 3 is 9, and 9 minus 3 gives us 6. So we have our first limit. Now we need to evaluate our other limit. So we have the limit as x approaches 3 of x squared minus 3x plus 6. Since this is a polynomial and 3 is in its domain, we can apply direct substitution. So we have 3 squared, substituting that 3 in for my x, minus 3 times 3 plus 6. 3 squared is 9, 3 times 3 is 9, so we have 9 minus 9, which is 0, plus 6, which gives us 6. So our limits are equal to each other. So we can just make a little concluding sentence. So since 3x minus 3 is less than or equal to f of x is less than or equal to x squared minus 3x plus 6, when x is near 3, and the limit as x approaches 3 of 3x minus 3 is equal to the limit as x approaches 3 of x squared minus 3x plus 6, and those are both equal to 6, the limit as x approaches 3 of f of x is equal to 6. And I've run out of room by Squeeze Theorem. The important part here is that you're showing the two parts of Squeeze Theorem. So showing this less than or equal to relationship when x is near 3, that you're showing that your outer limits are equivalent to each other, and that you're concluding that because these two things are true, your limit is also equal to whatever these two things were equal to. And just make sure that when you use the Squeeze Theorem, you're saying that you're using the Squeeze Theorem. Here's another way to look at Squeeze Theorem for this problem. Same problem, still Squeeze Theorem, just a different way to go about it. So we have this 3x minus 3 is less than or equal to f of x is less than or equal to x squared minus 3x plus 6. Now, taking a limit is very similar to an operation. So just like you could add 3 to each piece of this, add 3 to each piece of this inequality. You can also take the limit of each piece of this inequality. So we can take the limit as x approaches 3 of this 3x minus 3, and the limit as x approaches 3 of f of x, and the limit as x approaches 3 of x squared minus 3x plus 6. So we can take the limit of each part of this inequality, where that limit as x approaches 3 is coming from the fact that we're trying to find the limit as x approaches 3 of f of x. Then we can evaluate the limit for each piece. So we have the limit as x approaches 3 of 3x minus 3, and we can use direct substitution there. So we have 3 times 3 minus 3 is less than or equal to the limit as x approaches 3 of f of x. Can't evaluate that one yet, we just don't have enough information. Which is less than or equal to, we can use direct substitution again. So this is less than or equal to 3 squared minus 3 times 3 plus 6. So, and then we can just keep simplifying this. So 3 times 3 minus 3 is 6, which is less than or equal to the limit as x approaches 3 of f of x, which is less than or equal to, 3 squared minus 3 times 3 plus 6 is also 6. So we can see that the limit as x approaches 3 of f of x is squeezed in between these two values. It has to both be greater than or equal to 6 and less than or equal to 6. which leaves us with it having to actually be equal to 6. So we can conclude that the limit as x approaches 3 of f of x is equal to 6 by Squeeze theorem. If I can spell. Now, this is a little less precise in some ways, but it'll get the job done. Here's a problem that's more similar to how a mathematician would actually apply Squeeze theorem. So we have the limit as x approaches 0 of x squared times sine of 1 over x. Now, if we were to try to use direct substitution, we'd find that 0 is not in the domain of this function, so it's not going to work out. But if we tried, we'd get 0 squared times sine of 1 over 0. So 0 is not in the domain, which means that we can't use direct substitution in order to evaluate this limit. We're going to have to do something else. The nice thing about this not so nice problem is actually the tricky part. It's the sine function. What you see here is the graph of the function sine of x. And what you should notice is that the outputs for sine of x are stuck between -1 and 1. So no matter what we put inside of a sine function, the outputs are trapped between -1 and 1. So that means that in addition to sine of x being trapped between -1 and 1, sine of 1 over x is also trapped between -1 and 1. And though this doesn't quite look like our function yet, we do have some sort of scenario here where we have an inside function trapped within some bounds. So let's put that to good use. Let's use our -1 is less than or equal to the sine of 1 over x is less than or equal to 1. This looks pretty similar to this x squared times sine of 1 over x. We have a sine of 1 over x, but we're missing the x squared. So we need to figure out how to make it so this sine of 1 over x looks like an x squared times sine of 1 over x. And that means that we're going to need to multiply by x squared. But we have to be careful when we're dealing with inequalities and multiplying by things. We know that inequalities remain true. And you want to note this as you're doing this type of problem. When multiplied by a positive number, so that means we can only multiply each part of this inequality by x squared if x squared will always give us a positive number. And luckily, x squared is going to be greater than or equal to 0, so positive enough for all real numbers. This means that we can multiply each part of this inequality by x squared. And when we do that, we end up with the inequality negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to x squared. And now this is looking far more like Squeeze theorem. We have the first part of Squeeze theorem. Now we just have to find the second part of the Squeeze theorem. Let's see. We want to find the limit as x approaches 0 of x squared times sine of 1 over x. So let's take the limit of each part of this inequality. So we have the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared times sine of 1 over x, which is less than or equal to the limit as x approaches 0 of x squared. We can then evaluate the limits of our outside functions because they're polynomials and zeros inside their domain. So we have negative 0 squared is less than or equal to the limit as x approaches 0 of x squared times sine of 1 over x is less than or equal to, now we have to directly substitute 0 into this x squared, so is less than or equal to 0 squared. Well, negative 0 squared is 0, and 0 squared is 0, which means that this limit is stuck between 0 and 0. It has to be greater than or equal to 0 and less than or equal to 0, which means it just has to be equal to 0. So the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0 by Squeeze theorem.